All right, we're going to get started here doing section 12.5. In fact, we're going to do 12.5 part 1 here. Change my sign there. So we're going to do part 1, we're going to do lines, and then in part 2 we'll talk about planes. So let's get started here. Here we have a line in 3 dimensions, and we're going to talk about parameterizing these lines. And so what this graph here is showing you is that if we have a line that passes through point P naught, this point right here, and our line is parallel with vector V, that any other point that lies on this line, such as this point P here, that if we draw a vector between these 2 points, P naught and this other point that we want to see if it's on this line, the only way that it'll be lined ultimately is essentially telling you that it's parallel to V. And we're telling you it's parallel to V if our new vector, P naught P, is a scalar multiple of vector V. In other words, whatever point we pick on here, say we come along and pick this point over here, if we want to know it's on there, we draw a vector from the point we know is on the line, make that into a vector like that, and if we can take V, say for example in this case we would take V and maybe multiply it by -1/3, so we would find that P naught P, this line, right, if this is our new point P here, maybe we'll call it P2 because we already had that other P over there, is equal to something like -1/3 V or something like that, all right, where it's a scalar multiple. If it's in the opposite direction, if it's pointing the other direction, then it's a negative. If it's shorter, then it's a number less than 1 that we're scaling by. And if it's longer, then it's a number greater than 1. If it's the same length, then just the number 1. So some scalar out there that can be multiplied onto V to give us our other line, and then that would tell us that this point is actually on that line. Now, keeping this in mind, we can come up with a vector equation for a line. The idea here is we have some vector V, which is essentially our velocity vector that is parallel to the line that we're trying to do. And so when we have this line, what this velocity vector V does, if that's J, that's I, that's K, is it tells us how fast and we're moving along each of the 2 components. So it's a vector V. So it's going to be something like Vx in the I direction plus Vy in the J direction plus V Z in the K direction, like that. And so when we have our line on here, let's make our line red. So we have some line coming through, right? That when we look at this vector V, it points along that line, vector V. So we're going to call this V, we'll make it purple. Okay, it points along this line, or at least, I'm sorry, I should say, is parallel to this line. Here's V, and essentially each of the components tells you something. So like, let's say this was 2, this was 4, this was -5. What it's telling us is, if Vx is 2, it's telling us every time we move 2 in the I direction, we have to move 2 in the J direction, and back 5 in the K direction. So something like that. It's telling us how fast they're moving, essentially relative to each other and overall. How quickly you would be moving along this line. And so, dependent on those, or some scalar version. So if this was like a, what did I have? I don't know, I just erased it. Let me see if I could. If I have a 2, it could also be that if I moved 1 in this one, I'd be moving 2 in this one and -2.5 in that one if I cut them all in half, you know. But it's just some sort of ratio of how much you're moving for each one of them. You can imagine that, you know, the larger a value is, it's going to change what angle this is at. If these were all 1s, then we'd essentially have just the identity line that would be just, you know, moving the same amount in every direction, right? So here's our axis, and this would just be kind of coming up right in the middle, right in between them. And then the next thing we need to do is worry about how much is it offset. And that's what this R naught is for. All right, this R naught here is a vector that can basically be any point on the line. So some point P naught on the line, P naught is on this line, and we have a vector that points from the origin out to that point P naught R naught, And so essentially what we have is we have this part moving along as t changes. As t gets bigger, it tells us how much of a step to take. So if t is, so we had these numbers here. What did I have? 2, 4, negative 5, something like that. 2i, 4j, minus 5k, something like this, right? And then if we multiply this by t, what's happening is we're telling us, are we taking, if t is 1/2, then we're moving 1, 2, and 2.5. If t is negative 1/2, then we're moving negative 1, negative 2, positive 2.5, right? And if t is 3, then we're moving 6, 12, and negative 15 in each of those directions. Depending on what t is, it moves us along with different amounts of that. So we'd give it a value of t, and it'd tell us how far forward or how far back to move along that direction of v based on t. So then now we've added that t in, what we can do is look at this r0, and what we're going to do is we're essentially going to move somewhere along v, that's the vt part, and then we're going to use r0 to take our point and move ourselves up to the line that we want. So we can do, 2 times v, come out to twice v, and then move up r0, and we're on the line. Or we can go negative v, and then move up r0, and we're on the line. And then we could do a half of negative v, move up r0, and we're on the line. Or negative 3v, move up r0, and we'd be on the line. Okay? So that's the idea that we're doing there. We're essentially taking vt, which is a line that goes through the origin, and then we are shifting it by an amount equal to by r0. And this r0 doesn't have to be any vector in particular. We could have a different r0. It just has to point to any point on the line. So I could have an r0, say, that points straight up. Say this went through the k-axis like that. Say it does. I don't know if it really does or not. I just drew a line. But say I had a vector like that, and that could be our r0. And you could go a distance of v, and then r0, and a distance of 2v, and then that r0, that different r0. All of them, it's always going to put us back on that line as long as this vector we pick here, we have a lot of freedom in picking it, as long as it's actually based on a point that lies on the line we're trying to get to. Okay, so then how do we parameterize this? Well, I would say the biggest thing you need to do is understand this equation that I just went over. This one, super important right here. Really make sure you know and understand this one, because the next page is basically just an expansion of this. How do we parameterize this? Well, we expand it out. We have r0 plus tv, right? So v equals r0 plus t times our vector v, right? Where these are our vectors here, and t is just the scalars that we're going to move through, our little variable that we're going to be plugging in to get to different points on the line. And then r0 is just going to be like r0x in the I direction plus r0 y in the j direction plus r0 z in the k direction, right, plus t times vx in the I direction plus vy in the j direction plus v, they're using 1s and 2s and 3s, and I'm putting x's and y's and z's. Let me change it to the 1s and 2s and 3s so it matches up. Sorry. Let me do that. The 1 is x, the 2 is, is y, and 3 is z, and anyway. Oh, and they used x naughts and stuff like that. Boy, I'm just going to rewrite this whole thing here. Sorry about that. This is going to be r0 is going to be x0 in the I direction plus y0 in the j direction plus z0 in the k direction plus t times, and then what we'll have here is v1 in the I direction plus v2 in the j direction plus v3 in the k direction. So how does that compare to what I was writing before? This is x, this is y, this is z. I just did r sub x, r sub y, r sub z. So I just used a different notation. And then this is vx, vy, vz. So anyway, we've got this here, And now what we can do is start actually combining the like thing, because this is you're just adding them together. So if we distribute this t through, right, what we essentially have is x naught plus tvt, tv1 in the I direction. That's adding this I component with that I component. And then you have y naught plus tv2, tv2 in the j direction, plus z naught, add the z components together, z naught plus tv3 times the k direction. Okay, and then there we go. That's what we have it. So this is how our x is changing, this is how our y is changing, this is how our z is changing. So this is x, that's that right there. This is y, that's that right there. And then this is z, that's that right there, okay? And we can go we have no restrictions on t here, so we can do whatever we want. But we have essentially parameterized it all from just knowing this first one right there and just expanding it out and combining like terms. So in my opinion, I would remember this one and know how to expand it from the previous page, or if you prefer, memorize this whole thing right here. I don't know. It's up to you, whichever works better. I think it's best to, though, again, like I keep saying, better to understand than to memorize. So let's take a look here. We've got a picture. Here's our vector v right there, and it's parallel to the line we're looking at. And then we have different points. We can really pick any point we want on there to create our vector to offset that v, right? Because to get to that line, we need, remember, we need our vector times t plus a displacement vector. So we can have r naught, right? Is that what we were using? R of t is equal to r naught plus t times vector v, right? So we can have this. And then what we can do is have our vector vt, that's going to be, this that's given to us times t, but this r naught can be whatever we want. We could make it this one. We can make it p naught. So in other words, we can have p naught, from the origin to p naught as a vector. I'm going to call this origin like that, O or something. And so we can make the vector O to p naught, that vector plus tv, or you can do O to p1 plus tv. Any one of these is going to work, You can keep doing that. You could use this one or whatever, as long as it puts you onto that line. So if you look at this, we could move vector v amount, and then we could move p naught. Say p naught was about like that, and that puts us on the line. That would be the p naught offset. Or we could have moved p1, which would have put us there. That would have been the p1 offset. Or the p2 offset would have put us like over here. This would have been the p2 offset. And any one of those puts us on the line, and we end up with something that looks different but is ultimately equivalent. Okay? So take a look here. Find parametric equations for the line through, so we have it going through this point, and it's parallel to this vector. So they give us the vector that it's parallel to, and they tell us to add the point on. Well, what we really need to look at is what? R of t, our function, our vector function as a function of t, and we have to have our position vector added on to our velocity vector moving along. So this moves us along the line, this offsets us to reposition the line. This gives us our slope and everything like that. This gives us our graph shift. And so we can do that pretty simply. Just go through and do what we did before. We're going to add on, essentially, go through and do this for each one. We're going to take the x component first, and so we'd get 2, and we're going to multiply it by t, so 2t, and then we're going to add on this negative 2. That's the r naught part, right? And so negative 2 plus 2t, and that's the I direction. And then we have to do the j direction, so plus. In the j direction, we have 0 there, so 0. And then in the j direction here, we have a 4t, so plus 4t in the j direction. And then in the k direction, we've got a 4, so a 4, and then we have a minus 2t in the k direction. And so if you look, here is our x, here is our y, and here is our z, just like what's right there. All right, this is just a 4t, that's a 0, that's gone. So 4t, negative 2 plus 2t, 4t right there, and z equals 4 minus 2t. Okay, so there you go. Just go through, know this thing, and start piecing them together. Practice, practice, practice. All right, this one asks you to find parametric equations for the line P and Q. All right, now this time it's a little different because they're not giving you, like they did here, they gave us a point, and then they gave us the vector is parallel to. Here they're giving us 2 points. Well, the good news is what we can do is use those 2 points to come up with a vector that points between them. And that's what we're doing right here. Take the difference between them, it's a vector that points from one to the other, and now that is a vector that is parallel to this line. Okay, so there's our vector that's parallel to the line just by using those 2 points and coming up with a vector between them. So I don't know what this is. So this is negative 3, positive 2, like negative 3, positive 2, 1, 2, and then down 3. So that's P, and then Q is positive 1, positive 1, negative 1 back this way, and then up 1, 2, 3, 4. So Q is somewhere like up here, wherever it is, Q. And so what we're going to do is just make a vector from P to Q, like that. Okay? And when you make that vector, this is that vector right there, and that is automatically parallel to our line because our line is just running through those 2 points. So it's parallel. So there we go, we've got that. And so it's parallel to it, and now we have a point and a parallel line. In fact, we have 2 points in a parallel line. So which point do you pick? And just like I was talking about back here, it doesn't matter which one you pick. You could pick this one, or this one, or this one, or any other point that you know is on the line, and the answers will look different, but they will be equivalent. So you look here, and they did it with point P. So this was point P right there, okay? Over here, they did it with point Q, all right, with point Q. And so you get 2 different things. You get an answer set here, a parameterized line there, and a parameterized line here. And they look different, but they're actually still the same line. Either one of those draws you along the exact same line, and so therefore they're equivalent. They just place you at a different point for a certain given value of t. But given all values of t, they map out all the same points. All right. Example 3, derive a parameterization of a line segment PQ. So the only thing that's going to be different here than the previous example is the previous example, the line kept going forever in both directions. So we could do all of t. So the goal here, though, is to do the exact same thing, find an equation for the line, but then limit t, all right, limit t such that, and put ranges on values of t such that we start at one point, go the direction that the arrow is pointed, and end over here, and we don't go outside it, okay? So you're going to do all the same things, get the same line, but then limit the t values to make sure you're staying and going in the direction that you want to go. All right, so let's take a look here. Parameterize the line segment. So here, doing the same thing. This is the same parameterization of this previous example right here. So we already have it done, okay? So that's that same one. So we can go ahead and start with the answer from the example a couple pages ago. But now what we have to do, again, do all the exact same thing. You have to worry about what happens to it as it goes through t. Well, if you notice, on the line, if this is our XYZ coordinates right here, which we get just from, that's X, that's Y, that's Z, if we put that together, we'd see that if we plug in t as 0, that gives us this point here, right? If this is 0, this is 0, and this is 0, we end up with -3 to -3, all right? Because this is the parameterization we made with point P. So that works right there. So at t equals 0, we're starting at point P. What does t have to be in order for us to end at Q? And if you try it, you would see that when t equals 1, you plug in 1 here, -3 plus 4, that gives us a 1. 2 minus 3 is -1, and -3 plus 7 is 4. That puts us on point Q. So we essentially found what value of t gives us point P, what value of t gives us point Q, and then we need to worry about everything in between there. We need to go from P, where t equals 0, then all the values up until we reach t equals 1, and then we're done. And so ultimately, it's the same parameterization part right here. We're just adding on this extra bit about limiting t to stay within our boundaries that were given to us. All right, here is an example about a helicopter. A helicopter is to fly directly from a helipad at the origin in the direction of point 111. All right, so let's take a look here. We've got our origin right there, and we're flying in the direction of the point 111. So whatever it is, go over 1, up 1, forward 1, something like that. Okay? This is our vector that we're flying in the direction of 1, 1, 1. Okay? And then we have to figure out, and then it has a speed of 60 feet per second. So speed is just the magnitude of v. All right? And we know then that we've got the length of the velocity vector, and we have the direction of the velocity vector. So to get the actual velocity vector, we can simply take our speed and multiply it by a unit vector in the direction of what direction we're going in. Well, we're trying to go in the direction 1, 1, 1. That is not a unit vector. That has a length greater than 1. So what we can do is do the vector 1, 1, 1 divided by the magnitude of the vector 1, 1, 1. And that gives us our unit vector that's pointed in that same direction, and that gives us our velocity vector, right? And so then what we can do, that gives us this v right here. This is what we wanted. And then what we can do is say, what is the position after 10 seconds? And now this is flying directly from the origin, which means a point on this line directly through the origin. We can just go ahead and say r naught, right? This r0 vector is the 0 vector, right? It's the 0 vector because it's going through the origin. And so really all we have to worry about is finding this velocity v vector, and we'll have that r of t is equal to the 0 vector, right? Let me write it actually out for you, is r naught plus t times the velocity vector. This r naught is the 0 vector. This t is that, and then our velocity vector is this thing up here, which we haven't figured out, which is going to be what? 60 feet per second. That's the v. That's the magnitude of the velocity, times vector 1, 1, 1 divided by the magnitude of 1, 1, 1, which is essentially vector 1, 1, 1 divided by the square root of 1 squared plus 1 squared plus 1 squared, which is 1 plus 1 plus 1, which is the square root of 3. All right, so that gives us our velocity vector, which means we have 60 over the square root of 3 feet per second in the 1, 1, 1 direction like that, okay? And so if we do this, we can go ahead and say, all right, well, that's going to be gone, and we can plug in our 10 seconds. So we'll end up with this. We'll end up with R of 10 seconds times 60 over square root of 3 feet per second. And so our seconds will cancel with our seconds there in the 1, 1, 1 direction, like that. And then ultimately, that gives us 600 over the square root of 3, which is what? 600 root 3 over 3 feet in the 1, 1, 1 direction. All right, I can get rid of this. This was just to tell me to stop here, because the next part's the planes. 600 divided by 3 is just going to be, it's going to be 200 root 3, and then it's in 1, 1, 1, so we can go ahead and multiply that in, right? Multiply this into there. And so the position is 200 root 3 feet, 200 root 3 feet, 200 root 3 feet. And that's the answer. All right, so let's go ahead and get through this last little bit before we get into the planes. This is the distance from a point to a line in space. And so if you think about this, what we're trying to do is find the distance from a point to a line. And the distance we want is that shortest distance between them, such that our distance is perpendicular to our line. It's normal to the line we're looking at. So essentially what you need to do is pick some point on the line right here and find this length. Now you could do this kind of geometrically like this, which is the idea that we can make a triangle out of this. See, we make a triangle out of this, and then you know this angle right here, and you use sines and cosines and find that the length of this side is PS sine theta. So you can think of it that way if you have that information and you know where all that kind of stuff is and you go through that. Another way to think about this is if we can come up with a vector v that is parallel to our line, we can actually do a cross product. Remember, cross products multiply perpendicular components. So if I have the vector PS, right, that's this vector here, and I do a cross product of it with the vector v, what I'm going to do is multiply the perpendicular components together. So if I look at the vector PS, I'll see that it has two components, right? First component is here, and the second component is here. Now, this component is parallel to v, so when we do the cross product, it's going to go away. That means we're ultimately multiplying this vertical component times v, all right? So that's a good starting point. However, v does not necessarily equal 1, and therefore it will change, either make longer or make shorter our resultant vector that we get. All right, it's going to scale it. Actually, it's going to be coming out of the page, so it's more like it's going to make it either longer or shorter than the answer we actually want. So what we can do here is not multiply it by v necessarily, but find our vector v and then make it a unit vector. Okay? And if we do that and we take the magnitude of it, we're going to have our distance. Okay? So that's essentially going to be the distance from our point to our line. So take a look here on the next page. And this is what we have. So what I just showed you on the previous page here, I'll even label it D. All right, that's that. Is I had D equals PS times, not times, but a cross product times the unit vector V, and the unit vector V and the magnitude of it. We want the length of it. We don't want the direction of it. And so this is PS magnitude crossed with V over the magnitude of V. That's how we get the unit vector, right? And so then the very next step is to simply turn it into, well, that was a bad line, to turn it into that. P cross V over V. All right, so you can memorize and remember it this way, or think your way through and know how to use this one right here. I personally am a use this thing to get it done. But if you're not the same way as me, then go for it and use that one right there. Just get it memorized and make sure you can do it, okay? And here is an example that you can look through to see how to do this. They're finding the distance from the point S to the line, and they give you a parameterized line. So you can go through and come up with the vector for the parameterized line, the vector that's parallel to it. Since there's this a 1 times t right there, that makes this just a 1 times I. Here we've got a 1 times t, negative 1 times t, so that makes this a minus j. And then here we have a 2t, so it's just a plus 2k. So this is our vector here. Remember, all the coefficients that went with the t's were just the coefficients that went with I, j, and k ultimately. And so that's what we get right there. And now you have your vector that's parallel to it, and you have a point. It's passing through the point what? Here's our offset point, 1, 3, and then this would be a 0 plus 2t, so 1, 3, 0. Okay, so we can just look at the parameterization, pick out a point on the line, and pick out what the vector, the parallel vector coefficients should be. At that point, go through, find the vector PS right there, do your cross product. Notice this has no I, so we just put a 0 in there for it. Do your cross product, P cross V, or, and then ultimately just divide it by the magnitude of V right down here. So you do P cross V, find the magnitude of this, and divide it by the magnitude of what V was. Or you could have done the other order where you did PS cross V unit, where you found the unit length of V first, or I'm sorry, the unit vector of V, the unit vector in the direction of V, and multiplied that together. All right, so that's pretty much it now for this section. After this, I had another little red X. I had the wrong one in the other earlier, but I've got that little red X to tell me stop there, because the next page starts doing planes, and I'll do that in the next video. So thank you very much. See you soon.